All right, everybody, we're gonna get started. So as y'all can tell, Martin's not here today. I don't know how many of y'all have gotten an email from him over the Reflector, but he had to step down as president due to personal reasons. So I guess today I'm acting as president today, but according to our bylaws, we have to hold a special election for for any vacant officer positions. So next month, we're gonna hold officer elections for club officers. I will not be here next month because I have prior engagements I cannot get out of. So I will get with.
You're elected.
I'm not gonna be in the bathroom, so I'm not eligible. But I will get with Mark and a few others so we can get that dealt with and running smoothly. So if anybody is willing or able to run and hold the position, please let us know so we can fill positions and so we can have this club continue as it should. Next, I think Anthony might have had an announcement or wanted to bring something up. So if you want to come on up.
Hello, guys. So normally I would tell you about our next Parks on the Air event in 2 months, but today, Crossroads is doing their first Parks on the Air event. We plan on going out back to Stephen F. Austin. Hopefully they chose the same spot because it was actually a pretty cool spot, nice and wide open, plenty of room to put up antennas. So if y'all want to go and support them as well, by all means, same spot, same park, Stephen F. Austin, starts at 10 o'clock, ends at 5.
What is Crossroads?
Crossroads is another amateur radio club, but it's more geared towards the southwest area and more west of Houston. They have their own repeater
network.
link network. Yeah.
I think they're more along the West Park Toll Road.
Yes. Yeah. But it's pretty good. It's a pretty new club, but they're pretty good. They a lot of them so far.
They're on 147.240 on Thursdays at 8 o'clock.
Yes.
So if y'all have never done a POTA activation or a Summits on the Air activation, go do it. It's a lot of fun. If you don't want to do it by yourself at first, if you're on Facebook, there's a Houston POTA Facebook page that our very own Anthony helps run.
Yeah.
So if you want to go participate in a POTA that other people run, so you see how it works, go see how they run it. It's a lot of fun. I think my first POTA with them, I ended up making like 40 or 50 contacts. So
Yeah. So if you do go to the Facebook group, Houston POTA, you'll notice that several other operators, they go out and they'll post it there. If I go out, I'll post it there. Tell you where I'm going. If you feel that I'm in your area, because I don't just stay at one park, I go around all the ones around Houston. So if you feel that I'm in your area and you want to come check me out and see how to do it, don't wait for our events. Come and check us out. The whole point of going out to Parks on the Air is to get out of the house and enjoy amateur radio, because guess what? You may have your station at home all set up and ready to go and know how to use it just by a push of a button. But can you take that station out of your house, go set it up portably and still know how to operate it? I don't know. Yes, Doc.
Number two, it totally is a good test for low power and field day. Second of all, price of gas, they ain't gonna get any cheaper. And I'm just gonna make this suggestion. The carpool, I'm gonna say one thing, the transit center, Northwest Transit Center parking lot is not just for parking to get on Metro. As also a place where people can gather to carpool 24/7. That might be, a bunch of us can go over here and park, one vehicle and then, and two, further out, attics, we can use the HOV lane because it's 2+, and then we got a clear shot to 99. That most of the bad traffic will be hit when we get to 99.
Perfect, perfect. Now also for the technicians, if you're worried about, oh, well, I can't use HF or I can't go out there. So think about this. 10 meters, 28, 300, 28, 500 sideband is where the technicians can operate. You can either buy a radio at home, set it up, or yeah, you over there tapping her to, come on, let's go. You know, so you can come out there and try it, or you can buy a radio at home and try it. You can build your antenna, or you can just come out to the parks where we are. We have multiple radios set out. Myself, today I only brought one, but myself, normally when I go out, regardless, I still take 3. No telling who's gonna show up, and I want them to see all the options of what they can get, so.
And
Come check it out.
for y'all techs, if y'all go to a POTA event or a
Field day.
field day event, especially that's put on by a club or a group, some of those operators might allow you to operate under their call signs on HF bands or on the general or extra bands. So go out and check it out, and they might be like, "Hey, come on up," and let them use. They might let you use their calls. So.
Of course, you know, and especially in the parks, if you catch me, I'll let you sit down and use one of my rigs. Just so you can get used to holding, being able to use other bands. 10 meters, sometimes it's dead, sometimes it's not. It's just like, okay, hey, who are we gonna talk to today? But some of the other bands, for sure, you're gonna talk to somebody. Yes,
The Facebook, what is it? Howard?
it's a group, it's Houston POTA, that's it.
Houston one.
POTA.
It'll be,
All one.
T, like Parks on the Air, POTA.
So, y'all check it out, especially go check out Cross Radio's group today, if y'all got time. They'll be in Stephen F. Austin State Park over there. What is it? Just on the other side of Sealy, I think, or near
The
Sealy.
second exit after the Brazos River Bridge.
There it is. So, and it's pretty neat. So check it out. I'll turn it back to Jeremy.
All right.
Thank you, sir.
Somebody has their speaker on, if they can mute it. Thank you. I don't think I have anything else. So, I'm gonna pass it over to our, past president, Stephen, for his presentation.
thanks, Jeremy. Good morning. And thank you very much to Anthony, Christy, and Corey for this great work that they're doing with Parks on the Air. They're spanning multiple clubs, so it's not just one club specific. They're reaching out to different folks, as we just heard. Crossroads is the group now. So, and Parks on the Air is a great opportunity to see rigs. Say you've been wondering about, I don't know, the Yaesu 710 or whatever, or the IC 7300, whatever. You might be surprised. You go up to Stephen F. Austin State Park, enjoy nature, and you get to see a rig and test drive it before you commit to a purchase or anything. So, can't say enough good things about the work, the great work that Anthony and team are doing. Right. So my name is Stephen Flowers. I have been here at the Oak Forest Amateur Radio Club. I'm spending time with Brazos Valley Amateur Radio Club nowadays, all around the area. And I'm going to talk to you, well, a bit about my background for folks that may not know. My background educationally is in physics, and I've been working for 30 years. I worked for 30 years with Halliburton as a wireline engineer, software development, real-time operations, and IT management. That's in a previous phase in life. Then I've gone into the next phase in life, which is current. And of course, given a choice, I always wanted to deal into electromagnetics, and that's amateur radio in a very applied way, very practical way, and very theoretical. So that's what we're going to talk about. From there, we're going to delve into something called antenna modeling. Now, antenna modeling is an area that maybe you've heard about. It's useful. It's not a solution to all of your problems, but it's a tool that is hopefully by the end of this talk, you're going to find that it's very useful to have in your arsenal. And so with that said, let's go ahead and get started. Let's say Slideshow and start from the first slide. Yeah. So the title, Wes Coleman. Yeah. So the title of this talk is Practical Antenna Modeling Using ManaGal. And ManaGal is the name of the software that we're going to be delving into. So our agenda for the talk, let's go through that first, is going to be what practical questions do we want answered by antenna model? Why are we doing this to begin with? Next, anytime we approach a problem as engineers or scientists or technically inclined people, we always tend to look at how was this problem solved in the past? What can we learn from past experience? So that's what we're going to go into. How was antenna modeling done in the past? Next, we're going to talk about a tool that is very useful in many areas, software options for antenna modeling. That's going to be the bulk of this presentation. But we're not just going to go into the theoretical part. We're going to go into practical stuff. So consider this a workshop part of the presentation. We're going to do a practical model of a vertical antenna, then a practical model of a dipole antenna, and finally a practical model of an end-fed half-wave antenna. So given that, we're going to just dovetail into what's next and leave it hanging there. So we start with this. What practical questions do we want to answer? Well, say, for example, we're amateurs and we're saying a question that we want to answer, which is, in which direction is our antenna's best transmission and reception? Right? So, for example, we want to go ahead and find out if I put an antenna out in my backyard in this orientation, what's the radiation pattern? And that's exactly what we're going to delve into here. Next, how good is our antenna's transmission and reception in a particular direction? Again, our backyard antenna has been laid out. What's the, what in a particular direction, say I want to transmit to the Northeast, to New York. So then how good is it in that direction, right? So there we're going to dovetail into this term called radiation gain, and it'll make more sense by the end of this talk. And finally, okay, will our antenna be good for DX? What is DX? DX, remember, is long distance communication. Say we're fed up with talking to the guys in New York, a lot of fun, but see ya. We want to go ahead and go past them and go all the way to Europe. So we don't have to change our backyard antenna orientation, but we want to go ahead and go past, that area, that initial stop that we were having DX contacts with, which is New York. Now we want to go to DX, which is outside of the country, into Europe. There we're going to talk about something called elevation angle, a very important parameter. And of course, no antenna is perfect. No backyard is perfect. So we're going to have a metal shed nearby. We're going to have, I don't know, something, an antenna pole or something to that effect, another house, a neighbor's house. So how will other objects affect our antenna? So for that, antenna modeling is going to be something that we delve into. As mentioned, we look at the past. How was antenna modeling done in the past, right? Because we think we got it all figured out. How was it done in the past? So I ran into this picture right here, and I just have to show it to you. This is not a Photoshop, okay? This is actually, if you look, by the way, at the footnote there, there's a reference to Popular Mechanics magazine. It was a very, very popular magazine in the past. Maybe some of you know about it. Popular Mechanics, April 1959, page 81, you'll see this plot. So it was not Photoshop. So as a matter of fact, this was built by the US Navy in a place called Point Loma in San Diego. And that structure that you see there, it's actually a tower that was purposely built at this circular pattern, or semicircular pattern. Furthermore, check this out. That tower was actually made of non-conducting material. So it's actually a wooden tower, or some more likely wood, back in the 40s or 50s when they were doing antenna modeling. And of course, there will be some conducting material there because that's what they're trying to do, as will become apparent here shortly. But they're trying to model the radiation pattern. From where, you may ask?
That tower, if you look real close, you can tell it's not metal. You can tell that those are like telephone magnets. You use those for power poles because they're not straight.
Yeah, absolutely. I mean, to me, it would look like a truss structure made of metal, but obviously to somebody that knows about woodworking and metalworking, they'll immediately see that there's something funny about that tower. Let me raise it to the next level. What do you see on the lower right-hand corner? Something even fun or weird. Doesn't that look like a small model of an aircraft carrier?
Yes.
If you notice right back here, this thing here.
Look at flat top.
To me, it looked like a flat top, right? Well, that's exactly what it is. So what was the US Navy all about when they were doing this? Well, first of all, you had engineers involved, and that pretty much should give it away. Engineers used brass ship models on a lead sea to model radiation patterns coming from their, in this particular case, look at this intricate model made of brass of a battleship. That's what it is, battleship.
Look like an hourglass battleship.
I was gonna, yeah, I struggle for the word, but yeah, so the point is what they're doing is they're going ahead and shooting E&M waves into this device, into this brass battleship by symmetry, essentially inferring the radiation pattern of antennas on the battleship itself. So very hardware intensive way of modeling the behavior of radiation, E&M radiation for their use, which was ships. So fast forward to today. Of course, we're smarter. We don't do that stuff, or do we? This is exactly what we're doing today. We still model in hardware. Now, in this case, you have a scientist there, scientists at NRL, the US Naval Research Laboratory in Washington, where they've produced a miniaturized radar antenna from CAD design, computer-aided design models, and 3D printing techniques. Now, so we're using new technologies, but we're still modeling in hardware. Now, in this particular case, this article, which came from, again, one of the current technical magazines, was seen to be a faster alternative to designing and developing radar antennas, faster relative to software modeling. So bottom line, if you're the government, if you have quite a bit of funds available to you, you can do these intricate setups over here and model your antenna behavior. Okay, so we're thrifty ham, so we don't do that approach. What do we do instead? Well, one thing that I want to point you to is software. We're not going to model antennas in hardware. We're going to do it in the software antenna model. And we're going to use one of the available packages. This one is called ManaGal. And right off the top, we're going to get that silly name out of the way. Why is it called ManaGal? Well, MM, AN, the AN is for antenna, and the second A is for analyzer. So MM, antenna analyzer. MM refers to Makoto Mori, who is Juliet Echo 3 Hotel Tango. He's a ham. As you'll see, all of these people are ham. So it was an implementation by amateur operators. The G from Gal is for Igor Gontarchenko, EL2KQ. I believe that's German. And the AL is for Alex Chevrolet, DL1PVD. Again, three hams got together. They came up with this ManaGal software. The one that I'm going to show you today is freely available. So you can download it without spending a nickel. If you want to contribute to the programming effort of these programmers, of these folks, go ahead and use or get the ManaGal Pro version for $99. And you will be at peace with the universe. Or you can use EasyNet Pro 7. Used to be quite a few dollars, now it's free. The thing with EasyNet, if you find it useful, please, by all means, go ahead with it. I found that ManaGal was just simpler. And but all of these programs are based on the NEC MiniNet software. NEC is National Electromagnetics Code, or these algorithms that the US government made some time ago. They're implemented in these software packages. So with that, let me pause for a second and see if you have any questions before we go into the practical antenna modeling part of the presentation. This is going to be hands-on. Let's see how ManaGal works. I'm going to crank up ManaGal here and we'll go see it. So any questions, comments? Okay, right. So here we go. See if we can do this. Jeremy, are we still sharing?
Yes.
Okay, so as advertised,
Actually, hold on. Let me just double check.
as advertised.
Yes.
First thing, perfect. The first thing we're gonna do is we're gonna model a 20-meter vertical antenna. So let me point out some things about this diagram that I'm showing you here. The hashed line at the very bottom is meant to show ground. So that's your ground plane. The red line extending vertically is actually our vertical antenna. And you'll notice a little red dot or red circle at the very base. That's your feed point. As indicated on the upper left-hand corner, the little red circle is the feed point. There we go. Displacement in the Z direction or in the up and down direction, we're going to say 5.1 meters. How did we guess this number? Well, there's a lot of little programs that you can get on your iPhone or on your PC to actually tell you how long a vertical antenna must be. But if you think about it, we're doing a quarter wave vertical. 20 meters is the length of the wavelength. A quarter of that, about 5 meters. So 5.1 meters is to give it a name. Also note that we're going to have radials. Anytime you have a vertical antenna, you have to have radials. The reason for that is beyond the scope of this talk, but trust me. So in this case, we're going to use 11 radials, about 10 feet to 15 feet long, each resting on the ground and uniformly arranged from the endpoint outward. So you'll have like a starburst pattern on the ground there. Okay, so enough talk. This is Managal. When you launch the program, this is the GUI, that the graphical user interface that you come up with. There's 4 tabs to it: geometry, view, calculate, and far field plots. And you start with the left with geometry. So we're going to go ahead and call this 20-meter vertical, just so we keep our modeling terminology straight. This file or this exercise is going to be 20-meter vertical. Frequency, we can select different ones, but let's start with the 20-meter band in 14150 specific. Great. First thing you do is you highlight X1. This is like an Excel spreadsheet. So you just hit enter and you get X1, Y1, Z1. The X, essentially the first point with a subscript 1. And then you're going to get a second point over here, X2, Y2, Z2. We're going to put here 5.1 meters. And remember, it was at the Z displacement. So we're putting Z2 is equal to 5.1 meters. Enter.
So
Great.
is Y2, Z2 related to R2D2?
R2D2 was our cousin. Yes, indeed. C3PO is the next level. Thank you for that. There's always one on the crowd. Okay, so we're wanting to use the view tab next to make sure we actually put something right. In other words, we didn't put something diagonal or, sometimes it happens. So for here, you can use the shift key and scroll down and you can move this thing around. Of course, it's a very boring design, so there's not much insight that we can get from this, but this is acting as a quality control that you're actually modeling a wire going straight up and down. And that you can go ahead and hold the mouse and just do this kind of stuff and knock yourself out, moving the shape around. Next thing we're going to do is we're going to put our cursor close to the very base where, remember, our feed point was going to be, and right click. And we're going to say add source to the beginning of the wire. Okay. What's happened right here, it's put a little circle, a little red circle there at the bottom. Again, the legend on your upper left-hand corner says the little circle means source. And when passing, we know that there's another red X, a little red X. That's for a load. In this program, we can actually model loads. So what's a load? If you remember, if you work with a Wolf River coils or an antenna that's got a little coil on the very bottom, that's a load. It's an inductive or a capacitive load. We're not going to do that in this exercise. So this is the first approximation. I hope after this, you download Managal and you experiment with it. That's what it's all about. So next we go to calculate. We're done with the view. Now we double check that the frequency is 14.15. Great. Ground. What ground is, we need to tell the program what ground we want to use. Free space? No, that's in the space station. If we're going to put this up in the space station, that's what we use. Perfect. That's if you have perfectly conducting ground, which in parentheses, it should be noted that if you're on the salt water on Galveston Bay, the middle of the bay without any substructures, metal substructures around you, you might want to model it as perfect. But for here, we're going to go with real. So next we click on ground setup. And here we have two parameters of interest, dielectric constant and conductivity of the ground. Okay, it's defaulting to essentially basic average ground. It's not going to be desert like what you would find in outside of El Paso or San Angelo or somewhere like that. It's very dry, and it's not going to be very conductive like it would be if you're setting this antenna right next to the ocean where you've got salt water work. So we're going to leave it at default, and we're going to click this box right here that says radios. This is what how you tell the program to consider quarter wave radios, right? So right here, we're going to say the number of radio set 11, say okay, and the height. Height is how high off the ground you want to put that feed. In this case, remember, our approach was going to be to put it on the ground itself. Remember, the little red circle is on the ground. So we'll go ahead and say, we don't want this displaced off of the ground. We want it at 0. Material. What is your antenna made of? You have different choices here. We're going to just select copper wire. Say just a basic copper wire antenna. And that is, as you say, that's all we need to tell the program. As soon as we click start, the program will go ahead and run. And just be aware that this can take a long time. I mean, remember, you're asking the computer to solve very complicated differential equations. So we click start and it's done. Okay, so what just happened is okay, your power of computing, you can design a nuclear bomb with these things. It's amazing. So it's that fast, and it just simulated all your equations for you. Okay. So what does this tell me? I'd like to see two parameters in here. So I'm going to point them out to you. Are the input impedance of my antenna 35 ohms? We'd like to be 50 ohms, but 35, yeah, it could be worse. And my SWR, assuming a 50 ohm impedance, is 1.45. Not too bad. So now, with that, we go to far field plots. And here you see the far field plots. This. And you see two plots. Remember from your technician exams, possibly you looked at the azimuthal plot over here, fancy word for this plot, which is really a view on the left-hand side as if a bird was overflying your antenna. So your antenna is over here in the origin at x equals 0, y equals 0, where I've got the cursor right there. And what you've got is you've got the bird flying way over your antenna, and he sees essentially a big blob down at the bottom, right? That's what he's seeing. Now, on the right-hand side, you have the elevation plot. What is that all about? Well, it's as if you took this view right here, and you took a chainsaw to it, and you go ahead and cut it right down the middle. So that's what the slice would be right there. So it's got the two lobes of a typical vertical antenna. You can hold the mouse down and see what the gain would be. Don't get too hung up on the gain values themselves. Just use them as a comparative measure. And here you can actually see at 5 degrees, which is your DX elevation, where you're at. Well, what's your gain at that point? Remember one of the things we said at the very beginning. Say we orient this antenna to go to New York, and we say, okay, well, how is it going to be going to the UK? In other words, past in the same direction as New York, but past New York all the way to the DX country over there. Well, that's where the elevation of 5 degrees would be. By the way, the 5-degree rule of thumb comes from Callum McCormick. Some of you guys might have heard about the fellow. Brilliant guy. He's a DX commander, the DX commander antenna. He makes those. So he's very keen on this program. So we can click, for example, an elevation and say 5 degrees, say okay, and that's the profile at 5 degrees. So that's the gains that you'd expect to get at 5 degrees. This would be for your DX right here. So great. So that's fine. But I really am more of a visual person. Can you model this in 3D, in 3 dimensions, right? Well, you can. Use this button right here called 3D Fast Fourier, and you end up with this plot, which is the donut plot that we'd expect from a vertical antenna. Again, you hold the mouse down, and you can go ahead and knock yourself out doing this kind of fun activity all afternoon long. So we'll leave that one alone. And that is the modeling of a vertical antenna. As simple as that. So we're not going to save it. We're going to move on. Next, we're going to go to the next slide, which is going to be the practical exercise number 2, modeling a 20-meter dipole antenna. Okay. Now, a dipole antenna, if you remember, dipole meaning 2, it's gonna be extending from your feed point to one side and from your feed point to the other side symmetrically. And we're gonna hoist this device up a certain height. Okay, so our exercise here is gonna be, again, I point out the ground plane. It's the line with the hash on the very bottom there. And the red line right here is my antenna. It's gonna be a displacement in the X direction of 5.1 meters. Again, why 5.1? Well, because it's a quarter wave and it's 20-meter band that we want to work with. And on the other side, you see the other side of your feed point, which is your circle, your red circle, just like before, is going to be another 5.1 meter. We're going to then take this dipole antenna and displace it in the, remember, up and down direction, your delta Z is going to be 10 meters. And that is going to be 32 feet. Something in parentheses we should say, we're talking meters quite a bit here because Managal works in meters. So you'll have to convert your measurements to meters. Let me explain. Let's go back to Managal again with this in mind, which is what we're going to model. And we're here, remember our 4 tabs. So we go to geometry always, start on the left. And we're going to go ahead and put in, remember what we did? 20-meter dipole. The title of our exercise. Frequency, we're going to leave it at 14,150, which is the default. And we're going to go ahead and say enter, right? Just like we did for the vertical. And notice here that it's X1 meter, Y1 meter. So it really works in meters. So we have to get used to that. And here what we're going to do is we're going to go in the X direction, in the minus X direction. Okay, we're going to go minus 5.1 meters. Enter. And then in the positive X direction, that way, we're going to go plus 5.2. So 0.1 minus 5.1 meters, 0.2, 5.1 meters positive. Okay. Now, as always, we go to view to do the quality control to see if it did what we told it to. It did exactly what we told it. Not a very interesting antenna, a piece of wire resting on the ground. We hover in the middle, right click, and just like before, we add a source to the center of the wire. As soon as we click that, we notice that the program has added a little circle, a red circle, which the legend up on the left-hand side says, hey, that's your source. So your source is in the middle. Something in passing, if we go back to geometry, remember we added something here on the top part, but notice the program has added something down here. That's the driving the source that we're telling you to put in. So it's wire 1 center. So we don't have to remember that. We just do it interactively in view. So after that, we go to calculate. And again, we check out that the frequency is at 14.15, which it is. The ground setup, we unclick radios because we're modeling a dipole. We don't care about radios. We leave everything default. We say, okay. The height. Now, remember in the vertical, we had the vertical feed point on the ground. Here, that's not going to be, we're going to have to have a 32.8 feet of height. So that translates to 10 meters. So we'll go ahead and say 10 meters. And for material, we're again going to go with copper wire. So again, that's all we tell the program. Now we tell it to start and we brace for the long time calculation and you're done. So there we are. So now we're getting, again, the 2 parameters that we care about are our input impedance. Ideally, we'd like to have it at 50. It's saying 73, and could be worse. Our SWR, 1.88, not too bad. So we'll leave it at that. And then we go to far field plots. We see now that the donut shape has sort of been squished on the sides there. And that's because this is a dipole antenna. So the dipole is going to have a different radiation pattern. Again, this is the left-hand side, is the azimuthal view. It's as if the bird was flying over our antenna. Remember, our antenna was in the minus X and plus X direction along the X-axis. So it's saying that along the X-axis, which is up and down in this direction, in this view here, it's going to be squished. Your pattern, the radiation pattern is going to be squished. Along the Y-axis, it's going to be elongated. So that's a typical dipole radiation pattern. And we get a little bit of this sort of a pattern right here. So this is giving us insight about what would work for DX and what would work for what we call cloud burning. Remember, cloud burning is a term that refers to when our antenna is aiming directly up into the clouds and it hits the clouds and it hits right close, it bounces right close to us. So say we want to contact Beaumont, you want a cloud burn, which is going to go straight up and straight down.
NVIS.
NVIS, correct. Does anybody know what NVIS stands for? The guy in the blue over there. I'm putting you on the spot.
Near vertical. It's, yeah.
You can't ask for that. That was not rehearsed and then we nailed it. So near vertical incidence something. So yeah, so near vertical, so it's gonna go straight up and straight down. Sort of like the water analogy, you're getting on a water hose and you're hitting something and bouncing straight down. So this one's gonna have a bit of a cloud burning. You notice the high elevation envelope. Well, the question is, how is it gonna work for DX? Well, remember, the 5-degree rule, we put in elevation, 5 degrees, okay, and we get that. So it works, but it's not so great. Now with dipoles, I believe if you go a bit higher, elevation wise, that if you hoist the antenna up higher, you may get a sweet spot over there and get a better result. But this is what this is. One last thing before we exit, and by the way, with this, you've already modeled 2 antennas because we're done with modeling the dipole. One thing to notice is that the radiation patterns are going to vary depending on which band you're on. Okay, so if we change the band, and we'll see that in the next antenna, but that does happen. So we'll go ahead and close this one.
Can you show 3D on that?
Pardon?
Can you show 3D on that one?
I just closed it. I'll show you the next one. Sorry about that. It was too quick. But that's a valid question. Okay, now we're going to go to the advanced exercise. Okay, this is the last one, promise. So this is going to be an end-fed half-wave antenna. Okay, so say for example, you're going to Parks on the Air. Okay, so this is my artistic rendering of a tree in Stephen F. Austin State Park. And you have, say, you can hoist an antenna up to 30 feet or so. Okay, and you're going to have your end-fed half-wave, remember, has a 49-to-1 transform. That's a little light blue box on the left-hand side there. Where's my feed point? Remember, the feed point is a little circle, the little red circle, right at the transformer. And then, well, yes, Steve, what's this red line that's sticking out, back here? Well, that's what we call the pigtail or the counterpoise of an end-fed half-wave. And you'll see maybe online that the questions about, is a counterpoise for an end-fed half-wave really needed? Well, I hopefully that will be answered here in this exercise. Again, just a note about the diagram here. The hashed line at the very bottom represents your ground. And that again is my artistic rendering of a tree at Stephen F. Austin. So there we go. So the measurements that we're going to have. Well, we're always told that the end-fed half-wave should be about 67 feet long. Remember from trig, you have, or actually algebra 2, is your hypotenuse. The hypotenuse of this right angle triangle is going to be 67 feet long. That's your red line right here. That's your driven element. And then that translates into a displacement in the up and down direction. Remember, the fancy word is delta Z, but up and down, it's going to be 10.218 meters. Where did I get that from? Remember, that's 67 feet, which is what we got off of the internet that everybody builds these antennas for. So, okay, 67 feet. And then that translates to an up and down of 33.5 feet. And your sideways displacement or your delta X is 58 feet. Translate that to meters so we can go into our modeling exercise. One last thing. End-fed half-waves, we're always told about that, hey, you need to lift the bottom, the transformer off the ground. So we're going to do that. We're going to say 1 meter, about 3 feet off the ground. So 3 feet here, we have a transformer, counterpoise back that way, and from here, 67 feet up. So let's see how that works with our friend Managal. And for that, we start Managal. Again, remember your four tabs. Geometry, view, calculate, far fields. Start in geometry. Name, and fed half-wave antenna. We're going to model it for 14150. Matter of fact, that where we found that online, it's actually said that this was going to be for a 15-meter resonant sweet spot. Well, they did say something online that, hey, this thing is going to resonate in various frequencies, but definitely for 15 meters. So we'll go to 21050. We're going to do the modeling for a CW 15-meter antenna. As before, hit enter right there. Remember, X1, Y1, Z1, we leave at 0. That's our origin. X2, let's go back to our diagram, was 17.68 meters. If you look at the very bottom there, between the tree and our feed point, 17.68. So we'll go ahead and put in here 17.68 meters. And then for your up and down, up the tree there, 33 feet, which translates to 10.218 meters. Okay, so we'll put in here 0.218 meters. Return. Next, we go to view, and we see that what we thought we put up, we did put up. I mean, it's sort of, it's on the XZ plane back there, and it's just a wire like that. Remember, our driven element, our feed point is going to be right here. So we right click, we put our mouse on the very bottom there, and we say move or add the source to the beginning of the wire. And again, we see the little red circle down there. That's our feed point. Again, refer to your legend up in your upper left-hand corner. Okay, that's your source. Perfect. Now we go to calculate. We double check the frequency, 21.05, spot on. Real ground, we don't have any radios. We're just going to have a counterpoise or something, maybe. We're trying right now we're modeling without a counterpoise. We'll see how that works. So no radios, average ground, height above the ground. We don't want it at 10 meters. We want it, the smallest one is 3 meters. So we'll go ahead and change it down to 1 meter. And the material is going to be this copper wire that Anthony Morone has got for us. And it's a green copper wire, 67 feet. He actually did that for our field day exercise last year, and it was a success. It was very good results for people that built that antenna. 67 feet of copper wire. Great. So now we say start. Okay, this is when you start saying, okay, I don't believe in math. This is terrible because my SWR is 27,802. Calm down. What are we telling the computer to do? Well, we're telling it to see an SWR of 50. But remember, we have a 49-to-1 transform. Now, if somebody can go ahead and take a calculator and multiply 49 times 50, and anywhere, we can bring a calculator up here. But if somebody can beat me to it, 50. 49 times 50. What number do you get?
49 times 50?
2450.
2450. So bottom line, that transformer is going to take 2,450 ohms and bring it down to 50 ohms for us, which is what our radio likes. So when we're telling it, hey, model an SWR of 50, we're not telling them the truth. We need to change that. So we go to setup, and we say the standard impedance, change that from 50 ohms to 2450. Enter. Okay, great. Okay, now we're breathing again, but it's still pretty lousy. I mean, we went from 27,000 now down to 574, which is 1 to 574. That's not good, right?
It's 10 times.
Pardon?
It's about 10 times.
Yeah, it pretty much stinks. So we don't want that, right? So before we go into far field, let's improve our modeling a little bit, right? So one thing we can do is we can go ahead and add that second item that we were talking about, that counterpoise. So remember, we're going to have a coils going back to our radio. So that's going to be our counterpoise. And it's going to be, okay, let's go ahead and model that wire. So we go to the next line there, hit enter, and we say the origin is at 0, 0, 0, but X2, remember from here, you've got your 49-to-1 transformer, 67 foot into that tree. This way, you're going to have 10 foot of wire as your counterpoise. So let's call that -3. Why -3? -3 meaning 3 times 3 is about 9. So yeah, about 10 feet, something like that. So now let's go back to view, see if it did exactly what we told it to. It seems to have done exactly what we told it to. Again, view we use as a quality control of what we just did, where we just told the program to draw. Click on calculate, and now we say start. Well, that's a heck of a lot better. So just adding a counterpoise of about 10 feet, this is rule of thumb. I mean, we haven't done any calculations. We came up with this right here. Okay, 2.92, could be worse. But now I'm going to show you something interesting. And hopefully this is worth the price of admission to this talk. There's this button over here called optimization. Optimization will actually do tweaks to your geometry to go ahead and optimize mathematically the parameters that you want to improve something for your intent. Great, that's a lot of talk for what? Well, bottom line, the top part right here, the top box, is what we want to optimize. So we have to tell the computer, optimize for this. The bottom part down here is what we tell the computer, hey, you can tweak this to optimize the top part, right? So these sliders right here go from least important to most important. To the right-hand side is when we tell it, very important for you to consider. So SWR, very important. Match, very important. And the other guys, JX, no idea, don't care for it. Front to back ratio, yeah, don't worry about it. Gain, don't worry about it. So we're telling it to optimize for SWR match. And then remember, as with any program, we need to tell it, okay, what can you optimize? This is where we add the two wires. So we click here on type, wire. It's going to say, okay, wire one. And we're going to say, wire one, remember, was the one that had a delta X and a delta Z. So we're going to go ahead and say X2. And then it's already picking up 17.68. Next, we say, optimize the other parameter for wire one called Z2. Here, it's going to 10.218. Now, he's going to optimize from -2 kilometers to +2 kilometers. So that's a little bit too crazy. So let's go ahead and change that to 0. We don't want to go negative on our wire in the X direction or in the Z direction. And we don't want to go 2 kilometers. We're not, it's 67 foot for crying out loud. We're not going to go 2 kilometers. So let's say 50, just to be nice. And 50. Remember, these are meters. So that's about 150 feet that we're allowing the program to operate. And furthermore, we're going to optimize one last thing, the wire. Now this one's going to be wire 2. Remember, wire 2 was your counterpoise. Wire 1 is your 67 footer. Wire 2 is your counterpoise. So we say wire 2, and it only had an X2, so we optimize X2, and the program immediately says, hey, right now it's at -3. So okay, -3 meters. We go ahead and tell it, you can go to -10 meters and go to 0. So this is the advanced part of the modeling, okay? You're telling it what you can optimize and what do you care to optimize for. You click start, and now the program is actually doing some crunching for it. He's actually changing these values, and he's going ahead and coming up with something. So he's optimized your antenna and giving you a resistance of 2087. Remember, we wanted that to be 2450. It's a lot closer. And your SWR is now 1.5. Something you can live with. If you go back to geometry, it's gone ahead and changed your values. Remember, we had 17.68. Now the program is saying, hey, you probably want to have that delta X as 18 meters. And here's delta Z is fine at 10.218. And that counterpoise, you said it was going to be -3 meters. You might want to have it at -4. So this is the insight that you get from computer model. It's not telling you exactly what to do, but it's telling you, hey, you might want to do this 67 foot a different direction, a different dimension, and also for your counterpoise. You might want to have it longer. So that's what we're getting. Now you can play this game more and more. You can tell it to optimize or tweak some more values, but we're going to call it at 1.51. So now we say start, because so far we just ran the optimization. By clicking start, you're actually writing it to the database there. And then from there, we go to far field plots. Now we get this. So at this point, it's quite different than what we were seeing before. If we go to 3D fast Fourier, you get a bit more of a complicated pattern. And at that point, you're seeing that you're going to have dx. Now, you remember the 5-degree rule. So we put elevation, 5 degrees, and we start saying, okay, at this point, I get the most gain, which is quite good. There's a null right there. There's another good point right there. And the dx over here at 5 degrees is showing that it's going to be not bad in that direction. So in this direction here, is where I'm finding the best DX. So it's telling you at which direction you're going to have the best DX.
Since you're modeling this, but did you pick a north? Did you see the direction?
At this point, we haven't told it. It's all relative to X and Y. So if you want to align your X and Y with northeast or northwest, northeast, this way. So then you can go ahead and say, okay, my backyard has this. So it's just telling you relative to whatever you define as your X or your Z, or X or Y direction.
So at the park, what's your preferred directions?
Anywhere I can throw it up in a tree. Cause really,
But because it's ground up.
at some points when you're in the field, you can get a compass out, you can go, the element, the radiating element up in a tree. I've got it east and west. I've got mainly east side. There's more amateur radio operators on the east side of states. You do get some over the mountains in California, but it's pretty fun.
Thanks.
So let's just take a step back and see what we've actually done just now. We've modeled the vertical in 4 steps. 1, 2, 3, 4. Hopefully that came across. We've modeled a dipole in 4 steps. Geometry, view, calculate, far field. And we've modeled a pretty hairy antenna, pretty difficult, called an end-fed half-wave, in a few steps in which we actually had to use something called the optimization engine of this program. So with that, I'm going to conclude the talk, and hopefully this has piqued your interest into something that is freely available, and it's only as complicated as you want to make it. If you just want to say, okay, I've got an antenna in this direction, a dipole, but I've got my friend's house. It's about, I don't know, 5 meters that way. And I bet you that house is influencing. Well, if it's metal, you could probably simulate it by using a wire, just another wire off to the side. How do you do that? You go to geometry and you go to one of the new lines. Remember, we were saying X, Y, Z, 1. It's always the origin. It's always a 0 point with your feed point. In this case, you'd say, my neighbor's got a flagpole, or his house is 10 meters that way, 5 meters that way. Go ahead.
And we had fellow John who was the CW around the world in very low power. And he said his lawn wire was a quarter mile long. And I know that even at field day at the Red Cross, the lawn wire was always the most accessible. Could you put a lawn wire on your file and see what it can show us?
Absolutely, absolutely. It's just a question of entering a different value for delta F. We enter 17.68 meters. You can go ahead and translate that and definitely model it. The other thing, though, to be aware of is you want to be aware that this is giving you the mathematical ideal situation. Models are only as good as the inputs that you put in. It's solving equations for it blindly and very efficient. But beyond that, it's going to have to be your intuition. So it does the math. The physics is up to you. Your intuition is applied mathematics, if you think of it that way. Go ahead.
So have you tried to model multi-element vertical antennas?
Yes. The one that got me into this program was the DX Commander. DX Commander, if you haven't heard about it, is Callum McCormick's Commander. That's his great moniker. And he's got a company in the UK, provides essentially what it is. It's a fiberglass pole, about 30 feet, 10 meters, we're saying now. Tall, extendable. And then you've got vertical elements. So there was actually a Managal file that you can go on. So I think it was a Discord site or something. Hey, Callum, can you pass me the Managal file? So you just load their file and you can actually model the DX one, or you can build it, with this on your own, and you model for different frequencies.
So he's guaranteed a YouTube channel too.
He's got a YouTube channel indeed. He's a very, very accessible person.
I had another question about your grounding situation with the program. If you were able to get the ground parameters, what was that, connectivity and dielectric? Yeah, you're able to input them in there. Will it change the model as well?
Absolutely, absolutely. So that's a very good question that Anthony's bringing. And that was actually the topic of a BVARC newsletter article that I wrote 2 months back. And that was the effect of salt water on, you keep hearing these guys saying, hey, I went to the beach and I was able to DX all the, with 5 watts, although it was actually no problem. Mike had 5 NPM, another colleague saying, I went to Bolivar over there out near Galveston, and with 5 watts or something, he was able to reach Grenada or the other side of Grenada, close to Trinidad and Tobago. And the reason being because of the salt water. So that got me thinking, well, can we model salt water? Well, remember, let me show you in this area right here and calculate. When we went to ground setup right there, we didn't delve too much into these 2 parameters, but there's dielectric constant and the millisiemens per meter, the conductivity of the ground. If you go into the ARRL antenna book or in different places, you'll notice that, for example, for salt water, that conductivity goes to 5,000. It's 5 for average ground. It's about 500 for freshwater. So if you're close to Lake Conroe or Stephen, and up there by Huntsville State Park, where there's a lake and all that, you can actually model the effect of the freshwater, which is better than average ground. You go to West Texas, you have to drop that number down to 1.0 because the conductivity is pretty lousy in very dry areas. So the point is, you can actually model these things, and you can have a lot of fun giving you insight and proving or disproving, according to theory, what you've heard about. Yes, sir.
Is there any advantage to make a dipole 6 meter or 10 meter rotatable?
Yes, there is, because it is somewhat, again, we'd have to go to the model at that particular band. And, but it is somewhat direction. The dipole is somewhat direction. So essentially the way you orient it does make a difference. Because remember, you remember it sort of looked like an 8, right? Or it was sort of like that, right? So imagine that where the 8 goes by the center, that's a null. What if you remember from our technician exam, that was the null. So in that direction, you're not going to get anything. But you go 90 degrees off, you're going to have one of the big lobes of that number 8. You're going to be pretty good here and pretty good in that direction. So say you move, so over here and over here, you're getting, I don't know, Georgia and California. You don't want to talk to the Georgians or the Californians. You want to talk to the Northeasterners. Well, if you can rotate, if you can move somehow your dipole or string it up this way, then you could get Tijuana and New York. So that would be maybe.
I mean, all
Like the dipole was that directional. It looked, I mean, there was a little bit of a node on each side, but not much.
The dipole, it turns out, is well, one thing to note about these things is, let's go over here right quick, and hopefully I can show you. Say, for example, we just went through the MFET halfway, but this is going to have a relative, it's going to have bearing on that question. If you changed the bandwidth, I'm sorry, the band, say we go to 20 meters and we click start, nothing else has changed, nothing up the sleeves. We click that, 1.12. So this is telling us, according to our model, you remember the 2 parameters we look here after the computation. Resistance 2668. We want it to be 2450. So that's pretty darn close for a 49-to-1 transfer. SWR 1.12 doesn't get much better. But if you look at the far field plots, this is a different animal than the one we got before. So depending on the band that you're in, that dipole is going to have a different, or any antenna is going to have a different profile, different radiation profile. Also with dipoles in particular, as I'm sure you know, it depends on how high we hoist the antenna. If you have a dipole that's quite close to the ground, many experienced hands will tell you that'll make a heck of a cloud burner. Again, that NVIS terminology that we heard. In other words, most of your energy is hitting the ground and going straight up into the clouds and being great for having the local nets on HF, if need be, local being up to Louisiana. But if you go a bit higher, there's going to be a sweet spot, maybe about a wavelength, half a wavelength out. And at that point, you're going to be doing the best DX work for that jump.
To show the directionality, do you mind flipping between the view tab and the far field plot?
Yeah. So in this case right here, let me see if I can do this. I don't have a mouse here somewhere. So we're going X plus X and minus X against the XZ plane. And if we go over here to the far field plots, X plus X and minus X. So the lobes are in that direction. Okay, we be fast forwarding, we start seeing plus X. The red is the X. By the way, in here in the 3D plot, that light blue line that you see right there is actually around 10. That's the diagonal light blue. So we're right where the antenna is, we seem to have a null. But right on either side of X, we have those 2 lobes right there. And we have two additional lobes going up into the cloud burning territory. Furthermore, another one that I find very interesting is this massive horizontal lobe in the negative X direction. That's the reason I find it interesting is that you tend to see that it's sort of flattened. It's sort of close to the ground, which hopefully by the end of this talk now, you're realizing that it's close to 5 degrees, which is Dx. So if you want to go to that long direction, say you've got your 67-foot element here, and you're going to be working in 20 meters, that's say from here to that. So that in that direction is minus X. That's where it's going to be giving possibly good Dx. So, if you can string it up instead of that tree, you're going to be going there, which is New York, which is the one you're trying to hit, or whatever your objective.
Dipole, you have it straight across. But normally with dipole, you have it in very deep. Is there a way to model that?
Absolutely. Absolutely. Remember, we told it where our origin was, and just for simplicity, we just said plus X and minus X. You could say plus X minus Y, and now you have a slope, and minus X and minus Y, and now you have another slope, a symmetric slope. And then you hoist it by clicking on this in the calculated field. We tell it at the height, and now you have slope. Because remember, the height is going to be the height of your peak clock. Yes, sir.
Does it take into account refraction of the ionosphere?
No, it does not. That is up to you. What this is going to tell you is essentially just the radiation pattern. Remember that first slide when we showed that US Navy wooden tower that looked like a Photoshop? Okay, what those guys were doing, if you think about it, now we're looking over here at these plots, and you're looking at the far field plots. And by the way, we're saying far field very liberally here, but far field means very specific, something very specific in terms of the mathematics. So you have to be far away to a particular length. By the way, there's an article in the BVARC newsletter this month that I wrote about the far field. So mathematically, where is it, depending on the way. And at that point, then it's going to say, okay, if you had essentially a bubble around this aircraft carrier, would be modeling, whatever, battleship, then that's what the radiation pattern would look like there. Now, what it extends to beyond, that is for ionospheric physics or atmospheric physics, which then is related to solar physics, which is another part of the hobby that's fascinating, but so hopefully that was confusing. Yes, sir. Not quite.
Is there a way of modeling like the twin lead stuff? Tuning stuff.
If by stuff you mean I have an antenna instead of
Twin lead.
I would say yes, because it's a single feed point, right?
I guess it would be.
If you have a single feed point, I would say yes. It's just a question of drawing these wired elements in this program.
But it's a parallel feeder in a kind of points.
Okay, so if you're talking about a parallel feeder, at that point, you might be wanting to simulate a load. Because at that point, you may have a capacitive load. And at that point, you have to simulate that. Again, your models are only as good as your intuition and what you're telling the program to solve mathematics.
Well, the program seems to be set up for a single wire or single line feed companies. What I'm saying is to be able to model something that would have like a twin lead.
Maybe that's a good point. Maybe that should be clarified. The program is not set up to just model one wire. Okay, what I've shown you here are 3 simple examples. So you can go ahead and take it as homework and model your heart's content, everything you want. This can model, you remember those lines that we're doing in the geometry tab? I can put multiple lines in there. I can simulate a DX commander by each one of those elements. I can put all kinds of wires in. I can put loads in there, inductive loads, capacitive loads, not just at the base, halfway, going up the middle, whatever. So you can definitely do much more complicated shapes than what I've done here. What I've done here are 3 introductory problems so that you can get the gist of it. So that from here, you can take it to the next level.
Steve, did you, when you modeled one with multiple wires, did you start seeing some interference? Some changes because of
The pattern would not behave like a vertical. I mean, a vertical, that we showed here is just an empty space. The vertical will behave like this. It does not behave like that with
it takes into account all those other wires.
So yes, it does.
Very cool.
Yes, it does. Very cool. It looks at it as interference because remember, they're not going to be driven elements, but they're going to be wire elements right close to it.
So I'll put it on my telephone poles if you do.
Yep. So it's good fun to do. Hopefully this piqued your interest. Again, this is introductory. From here you can take it and yeah, there's multiple videos online that will take it from here.
I was taking a test.
Yes, sir.
What's the name of the software?
Right. The name of the software is Managal. And we talked about that one at the beginning there. Managal. There's other softwares. Okay, there's EasyNet, and that's become free not that long ago. They're all using this National Electromagnetics code or something to that effect. So they're based on the same algorithms.
So the presentation was recorded, so if you want to go back and catch the first part of the presentation, go watch it on YouTube.
Yeah.
Later on.
And the price is right. Free.
And I do want to, since he didn't mention he did take a test, I want to congratulate him on passing his extra today, so.
Oh,
So tell congrats.
So you're gonna get your extra next, right?
So hopefully this was instructive and yeah, it's a lot of fun. And it just, again, it's your physical intuition that helps, that constrains the math. You know, the program is going to do whatever you tell it. Like, for example, simulate from -2 kilometer long wire to +2 kilometer long wire.
Jeremy, can I, I brought stuff to talk about programming radios. If I can get to the internet, I'm on Zoom. You make the presenter.
Yeah. If you want to come up here or if you want to do it from there. Yeah. While I'm switching that, let's see, participants, I'll make co-host. There you go. While Hal is setting up, I sent out an email, Thursday or yesterday. If you did that non-contest contest that Martin started earlier this year, and you brought your paperwork with you, give it to me. I have the prizes up here, so whoever made the longest contacts will get their prizes.
Pick whichever one.
All right. And for those that did participate and got the shortest contact is the next president.
So what I've got here is everybody have handhelds and program for repeaters. So I thought I would go ahead. We're gonna do this every month. Like every month I'm here for the meetings. I'll have chirp and it's whatever cables I have, program radios. So we'll do that at every meeting, and so that is if nothing else, it'll be a review for some, first time through for others, and we get everybody's radios up. Repeaters. Cool. So chirp is the software that will talk with radios. The very first thing you're going to want to do is going to get the cables, the correct cables from the company, because RT cables are really good, and they also have their own software. Because the chipsets are different, so the USB drivers are going to be different. So you need to get the correct driver. So here we are at Chirp. I've got two different radios I'm going to show today, but I will start with a Yaesu. Also, hey, just a second. Yeah. Jim's in here? They're there. Jim. So Jim got 100 on his extras. Okay. So I plugged the USB cable in, this RT cable, and it's not plugged into the radio at all. Okay, so go to Chirp and you say, okay, radio, I want to download from the radio is the first thing I want to do. And where it says port, that is actually, it found the device found the USB cable and is assigned it to a communication port for the computer. So it's the A2FT6. That's correct. So I'm gonna say, okay, everything's looking good. So I say, okay, now it says turn radio off, which I've done. Connect the cable. This one happens to go into the top mic plug-in. It says press and hold the Monty switch while turning the radio on. Well, that's something you have to know about your radio. It happens to be the top button on the side underneath the push to talk button. I'm holding that down. I turn on the radio. Turn on the radio. And what happened? Whoops, we'll try that again because I did it wrong. Let's try it. Okay, it comes, you can't see up there, but on the radio, it becomes it has a menu that it's a different categories. And so it says dial up to F8 clone. So F2, 3, 4, 5, 6, 7, 8 says the word clone. And it says hit the FW key once. And it's ready to clone. Okay, so the radio's ready. And it says, after clicking OK, press the talk switch once. So I will do that after clicking the OK. I did that. And we'll sit for a second. All right, failed to communicate. This is not unusual. I'm glad it's not a perfect time because we should go through the steps again just to be sure we did everything right. Okay, so okay.
And if you don't use it that often, be sure you get log into it every once in a while and do the updates on sure. Because they occasionally they will do big updates or minor updates. So if you're gonna go to like a field day or a CODA, whatever, without internet access, you want all those programs to be as up to date as possible to program your radios properly.
Correctly, and then when it does, okay, here it is. All right, so Hal's got he's using his Yaesu here, which is the Yaesus are a little bit more reliable in terms of data transmission through the communication port. So once you overcome the driver issue with the communication, then you follow the instructions, it'll pull up and then it'll start cloning the data.
First thing, you always want to clone it first, no matter even if it's a brand new radio. So it shows you all the rows and columns. So here's a loaded radio.
Right.
Go ahead, Mark.
So the way to be sure that the radio and the cable and the software may still communicate, but in order to get the information in and out of the radio, you got to make sure that it actually downloads directly from the radio. And as Jeremy pointed out, they change how the software communicates and where all the pointers are and stuff. So you got to have the new version of the software so that it reads the files correctly, and then also you can read it back in. So the first
every repeater will give you the information that they have about the repeater on but the repeater book and the club has a CSV file ready to be downloaded. The number one on there, that frequency is Simplex. That's why that one is.
So when it's open, you don't need a key.
So you can see up on the top here, it actually gives us a name for this download, a .img file. So it's an image file of all that information. So this is the first file that you're going to get from your radio, and you're going to want to save a copy of that. So if something gets scrolled up on the loading, you can always go back to the original image file of that radio.
Go up to the edit or file export.
Yeah, but I wanted to not skip something here. So the first step you're doing is you're pulling down off the radio. Then you're going to save that file, which is the IMG.
But before we break up, I wanted to bring up Field Day, which is in June. I know there's a few of us that want to participate, and I wanted to see if there was any interest from y'all to do a field day activity this summer, in June. Anybody?
Well, we just talking about field day. We have a standing offer to do field day at Red Cross, and we've done this ask.
I know there's a few of us that want to, that's a great idea. If y'all want to, if we want to do that, great. I know a few of us also want to go out and actually, you know, go to the field somewhere, set up radios and do set up antennas, radios and run off of either battery, solar, all that as well. So if y'all are interested in that option, please let me know. If you're interested in the Red Cross or just either way, either setup, please let me know if you're interested so we can get a poll on who's interested in which way y'all want to participate. Maybe we can do I know we tried it a couple years ago where we did it, I think we did it here and then also at the state park. So we can also do like the club call with the stroke 1 or a stroke 2. So if we do a split operation, we can do it in 2 locations if that's what y'all want to do, or if we have enough people to do it in both locations. So please send me an email through the Reflector, or if y'all, I'll send out an email asking that as well, so y'all have my email. So we can figure out who's interested in which setup. Again, next month we will have a special election for club officers. If you're interested, please let me know so we can know who's interested in running for positions. Yeah.
If anybody wants to do the Red Cross thing, they're welcome. If you want to do, someone wants to do another, but both options are there.
Right.
And if somebody doesn't want to do the outside sweats on, they can come in and put a nice air conditioning like the gym, use it at the Red Cross.
Right.
You can do both.
Right, and what we've done in what we did in the past, I think was at where did we go? It was Stephen F. Austin. Sounds like it. We did get one of those screen shelters, so we will have shade and electricity. So if you want to bring portable fans, whatever, whatnot, Anthony.
So how many vacant positions do you have?
So there are technically there are 4 positions for the club. Be it president, vice president, secretary, treasurer. Mark is holding the position of secretary and treasurer. But as far as for right now, the vacancies will be president and VP. Like I said in the email, I sent yesterday, Thursday or yesterday. I'm still willing to help out with, you know, the recording, the Zoom, the copying and where I can, but with, you know, the actual running of the club, it's you know, needs to be dealt with on a different level than Martin and I were able to do. So if anybody is interested, please send an email to me and Mark so we know what's going on. And we still have a meeting Monday night. I think you got the email between me, you, for the trustee meeting. So so if there's nothing else, yes.
Also, too, we got open positions now for net controls because on Tuesday nights.
So we can, yeah. So if anybody is interested in that and helping out as a net controller, please let Dom know, and yeah, let Dom know because I know he helps on that. But most importantly, we need to make sure we have our officers in place for the club moving forward. So if there's nothing else, I do have something. Yes.
So
I do have something. Just wanted to say, guys, great job, Jeremy. Excellent. He was thrown in the middle of it. You know, the president stepped away and he just stepped up and did a great job. Thanks.